Somewhere in the western Pacific Ocean, roughly halfway between the coast of Japan and the island of Guam, there is a patch of water that fishermen refuse to enter. It has no walls. It has no visible markers. There are no signs warning travelers to turn back. There is nothing, in fact, that distinguishes this water from the water surrounding it. Not to the eye, not to the camera, not to a satellite looking down from orbit. And yet, for centuries, the people who live closest to it have called it by a name that needs no translation. Ma no Umi, the Sea of the Devil. This is not a name given lightly. Japanese sailors are among the most experienced ocean navigators in human history. They have crossed typhoon-riddled waters for generations. They have built vessels capable of surviving conditions that would shatter most Western ships of comparable size. These are not superstitious people prone to fear without cause. Their maritime tradition stretches back more than 1,000 years, forged in some of the most violent waters on Earth. The coast of Japan is battered by typhoons, swept by powerful currents, and surrounded by seas that can shift from calm to deadly in a matter of hours. Japanese fishermen know the ocean the way a farmer knows soil, and still, they looked at this particular stretch of water and said, "Do not go there." The Devil's Sea sits within a loosely defined region south of Tokyo, stretching across a vast triangle of open water. Estimates of its boundaries vary depending on the source, but most accounts place it between Miyake Island to the north, Iwo Jima to the south, and a vague eastern boundary that dissolves into the emptiness of the Central Pacific. Within this zone, ships have vanished. Military vessels have disappeared without sending a single distress signal. Aircraft have entered the region and never emerged on the other side. And in at least one documented case, a research ship sent by the Japanese government to investigate the disappearances was itself swallowed by the sea it had come to study. That ship was the Kaio Maru No. 5. It was dispatched in September of 1952 with a crew of 31 scientists and sailors. Its mission was straightforward: sail into the Devil's Sea, gather data on the volcanic and seismic hazards of the region, and return with an explanation for why so many vessels had been lost in such a short span of time. The ship entered the zone. Contact was lost. No wreckage was ever recovered from the surface. No bodies were ever found. The Japanese government, shaken by the loss of the very ship it had sent to solve the mystery, officially declared the area a danger zone for maritime traffic. Not a mystery, not a legend, a danger zone. A formal, governmental acknowledgement that something about this water was deeply, fundamentally wrong. What makes the Devil's Sea so unsettling is not just the disappearances themselves, terrible as they are. It is the pattern. Over a span of roughly a decade and a half in the mid-20th century, at least 9 large vessels vanished in this region. 9 ships, gone, with no storms recorded in the area at the time of each disappearance, no mechanical failures reported beforehand, and no survivors to describe what happened. No oil slicks were spotted on the surface. No life rafts were found adrift. The ocean simply took them. Silently, completely, without leaving a single piece of evidence. And here is what most people never learn. The Devil's Sea is located almost exactly opposite the Bermuda Triangle on the globe. If you were to push a pin through the Earth at the approximate center of the Bermuda Triangle in the Western Atlantic, it would emerge in the Western Pacific, within the boundaries of the Devil's Sea. 2 zones of unexplained disappearance, sitting on opposite sides of the planet, mirroring each other like wounds in the surface of the world. This geographic symmetry has fascinated researchers and unsettled sailors for decades. Whether it is coincidence or evidence of a deeper geological pattern remains an open question. By the end of tonight, you are going to understand what the Devil's Sea actually is, why ships vanish in its waters, and why the explanations offered by science may be even more disturbing than the myths. You are going to learn about the geology beneath this cursed patch of ocean, about volcanic forces capable of swallowing vessels in seconds, about magnetic anomalies that confuse instruments and lead navigators astray, and about a seafloor so violent that it reshapes itself without warning. You are going to discover that the Devil's Sea is not just a legend passed down by superstitious fishermen. It is a real, measurable, physically active region of the Earth, where the rules of the surface do not fully apply. Before we get started, if you find these mysteries as fascinating as we do, take a second to like the video or subscribe. It is a simple action, but it helps this channel reach more curious minds like yours. The Pacific Ocean holds secrets that no other body of water on Earth can match. It is the largest, deepest, and least understood ocean on the planet. More than half of the world's oceanic volume is contained in the Pacific alone. Its trenches reach deeper than any mountain on the surface reaches high. Its floor is scored by volcanic chains and tectonic boundaries that generate more earthquakes and eruptions than all the world's continents combined. And the Devil's Sea sits at one of its most geologically unstable points, perched above a collision of tectonic plates, volcanic chains, and deep-sea trenches that plunge to depths where sunlight has never reached, and human technology can barely survive. The water above these features looks ordinary, calm even, on a good day. That is the deception. That is what makes the Devil's Sea so effective at what it does. What follows is the full story, not the abbreviated version found in listicles or 5-minute explainer videos. The complete unbroken account of what the Devil's Sea is, what it has taken, what science has found beneath its surface, and why, despite decades of research, parts of this region remain as unexplained today as they were when the first ships failed to return home. Now let us begin. To understand the Devil's Sea, you must first understand where it sits, not just on a map, but in the architecture of the Earth itself. The Pacific Ocean is not simply a body of water, it is the single largest feature on the surface of this planet. It covers more area than all of the land on Earth combined. Every continent, every island, every mountain range and desert and forest and ice cap, if you gathered them all together and placed them side by side, they would still not fill the Pacific Ocean. From east to west, it stretches more than 19,300 kilometers, nearly half the circumference of the globe. From north to south, it spans over 15,500 kilometers. Its total surface area exceeds 165 million square kilometers. That is roughly 1/3 of the entire surface of the Earth, covered by a single, continuous body of water that is deeper and more violent than most people will ever know. And the Pacific is deep, not merely deep in the way that a swimming pool or a lake is deep, where the bottom is visible or at least imaginable. The Pacific is deep in a way that defeats human intuition. The average depth of the Pacific Ocean is approximately 4,280 meters. That is over 14,000 feet of water pressing down on the seabed at every point. To put that in perspective, if you took Mount Rainier, the tallest peak in the Cascade Range, which rises to 4,392 meters above sea level, and dropped it into the average depth of the Pacific, its summit would barely break the surface. In many places, it would not break the surface at all. The mountain would simply vanish beneath the waves, submerged entirely, invisible from above, as if it had never existed. But the Pacific does not stop at average depth. Within its basin lie some of the most extreme depressions on the surface of the planet. The Mariana Trench, located to the south and east of the Devil's Sea, reaches a maximum known depth of approximately 10,920 meters at a point called the Challenger Deep. That is nearly 11 kilometers of water stacked vertically above the seabed. To grasp this distance, imagine standing on the floor of the trench and looking straight up. You would be looking through a column of water taller than the cruising altitude of a commercial jet aircraft. The surface, if you could see it, which you could not, because the light dies long before it reaches this depth, would be further away than many cities are from the mountains that overlook them. If you placed Mount Everest at the bottom of the Mariana Trench, the tallest mountain on Earth, standing at 8,849 meters above sea level, its summit would still be submerged under more than 2,100 meters of ocean, more than 2 kilometers of water above the roof of the world. That gap, 2,000 meters, is itself deeper than the maximum depth of the Mediterranean Sea at many points. The crushing weight of water at the bottom of the Mariana Trench generates pressures exceeding 1,071 bars, roughly 1,000 times the atmospheric pressure at sea level. To make this tangible, imagine the weight of 50 jumbo jet aircraft concentrated on a surface the size of a single human body. Every square centimeter of skin, every organ, every bone, would be pressed upon by a force that is almost impossible to survive. A standard aluminum soda can would be crushed instantly at these depths. The walls would collapse inwards so quickly and so completely that the result would be an unrecognizable pellet of crumpled metal. A styrofoam cup lowered to the bottom of the trench on a research cable returns the size of a thimble, every air pocket compressed to nothing. A human body, unprotected, would be lethal at a depth of just a few hundred meters. At 11,000 meters, the force is so absolute that even specialized submersibles must be engineered with precision measured in fractions of a millimeter. The slightest flaw in a hull, the smallest imperfection in a seal or viewport, and the ocean forces its way in with a violence that is instantaneous and total. There is no slow leak at the bottom of the ocean. There is only catastrophic failure or perfect integrity. Nothing in between. The Devil's Sea does not reach these maximum depths, but it does not need to. The waters within its boundaries are still among the most geologically violent on Earth, and the depths present are more than sufficient to hide anything that sinks beneath the surface. The region sits along what geologists call the Izu-Bonin-Mariana Arc, a chain of volcanic islands and seamounts created by the collision of the Pacific Plate and the Philippine Sea Plate. This is a subduction zone, one of the most powerful geological phenomena on the planet, a place where one tectonic plate is being forced beneath another, driven downward into the hot mantle of the Earth at a rate of several centimeters per year. The process sounds gentle at that speed. Several centimeters per year is roughly the rate at which a human fingernail grows. But the mass in motion is beyond comprehension. The Pacific Plate alone covers approximately 103 million square kilometers and is composed of rock tens of kilometers thick. Moving this mass even a few centimeters requires energy on a planetary scale. And when the motion encounters resistance, when the plates lock together along a fault line and the pressure builds until it exceeds the strength of the rock, the energy releases in a single catastrophic event. The result is an earthquake. In the subduction zones of the Pacific, these earthquakes can reach magnitudes of 8 or 9 on the Richter scale, among the most powerful seismic events that occur on the surface of the Earth. A magnitude 9 earthquake releases energy roughly equivalent to 32 billion tons of TNT, or approximately 500,000 times the energy of the atomic bomb dropped on Hiroshima. This energy does not merely shake the ground, it reshapes it. Entire coastlines can shift by meters in a single event. The seabed can rise or fall by tens of meters, and the displacement of the water above, pushed suddenly upward or pulled suddenly downward by the moving seafloor, generates tsunamis that can cross the entire Pacific in a matter of hours, arriving at distant shores with enough force to reshape landscapes, destroy cities, and end thousands of lives. The Devil's Sea sits directly above this collision zone. Beneath its surface, the seafloor is not the flat, stable plain that most people imagine when they think of the ocean bottom. It is a landscape as rugged and varied as any on the surface of the Earth, perhaps more so. Volcanic peaks rise from the depths, some of them climbing thousands of meters from the ocean floor without ever breaking the surface. These are seamounts, underwater mountains that are invisible from above but massive in scale. Between the seamounts lie deep fissures and trenches, slots in the ocean floor where the crust has been torn apart or pushed down by tectonic forces. Hydrothermal vents dot the seabed, releasing superheated water laden with dissolved minerals from the interior of the Earth. The water emerging from these vents can exceed 300 degrees Celsius, hot enough to melt lead, yet it does not boil because the pressure at depth is too great for water to transition to its gaseous state. One of the most significant volcanic features in the Devil's Sea is Myojinsho, a submarine volcano that sits beneath the surface south of the Byanese rocks. Myojinsho has erupted repeatedly throughout recorded history, and its activity has been documented by Japanese scientists since the early 20th century. In 1952, the same year the Kaio Maru No. 5 was lost, Myojinsho produced a series of violent eruptions that created a temporary island above the ocean surface. The island rose, existed for a brief period, and then sank back beneath the waves as the volcanic material was eroded by the sea. This phenomenon illustrates the extraordinary dynamism of the Devil's Sea. The seabed is not permanent. Islands can appear and disappear within weeks. The underwater landscape can change between one survey and the next. Submarine volcanic eruptions are fundamentally different from their terrestrial counterparts in ways that make them more dangerous to ships, not less. On land, a volcanic eruption announces itself with visible drama. Ash clouds rise kilometers into the sky. Lava flows glow red against the landscape. Pyroclastic surges race down the mountain slopes. The danger is visible and, to some extent, predictable. Beneath the ocean, the weight of the water suppresses many of these visible effects. An eruption can occur directly beneath a ship without producing any visible sign at the surface until it is too late. What the eruption does produce is an intense release of energy, heat, and gas into the water column. The gas, primarily carbon dioxide and sulfur dioxide, rises through the water as a dense cloud of bubbles. These bubbles reduce the density of the water they occupy. A vessel floating on the surface depends on the density of the water beneath it for buoyancy, the fundamental principle described by Archimedes more than 2,000 years ago. Water pushes upward against the hull with a force equal to the weight of the water displaced. If the density drops because the water is filled with gas bubbles, the buoyancy drops with it. The ship sinks lower. And if the gas eruption is intense enough, if the reduction in density is severe enough, the ship loses buoyancy entirely. It does not capsize, it does not break apart, it simply drops straight down into the aerated water column, pulled by its own weight into a medium that can no longer support it. The sinking can occur in seconds. There is no time for a distress call. There is no time to launch a life raft. The ship is there, and then it is not. This is not speculation. Experiments conducted in laboratory settings by oceanographers and naval engineers have demonstrated that water saturated with gas bubbles can reduce buoyancy by 30 to 50%. Model ships placed on aerated water in tank experiments sank immediately and vertically, with no listing, no capsizing, and no gradual settling. The behavior matches precisely what is observed in real-world disappearances in the Devil's Sea. Sudden, total loss of the vessel, with no wreckage remaining at the surface. Light penetrates the ocean in layers, and understanding these layers helps to grasp why the deep ocean is so profoundly alien to surface life. The top 200 meters of the ocean, known as the epipelagic zone, receive enough sunlight to support photosynthesis. This is the sunlight zone, the familiar ocean of blue water, coral reefs, and abundant marine life. Below this, from 200 to 1,000 meters, lies the mesopelagic zone, the twilight zone, where light fades to a dim blue glow before vanishing entirely. Below 1,000 meters is the bathypelagic zone, the midnight zone, where no sunlight has ever penetrated. The darkness here is not the darkness of a cloudy night or a deep cave near its entrance. It is absolute. It is the total absence of photons from the sun. The only light in the midnight zone comes from bioluminescent organisms that produce their own cold glow through chemical reactions within their bodies. These flashes and pulses are the only illumination in a world of permanent night. Below 4,000 meters lies the abyssopelagic zone, the abyss. Temperatures here hover just above freezing, between 1 and 4 degrees Celsius. The pressure is immense. The silence is nearly total, broken only by the faint vibrations of seismic activity transmitted through the rock below. And below 6,000 meters, in the deepest trenches and rifts, lies the hadalpelagic zone, named for Hades, the ancient Greek realm of the dead. This is the deepest layer of the ocean, found only in the great trenches that scar the ocean floor. The Isu-Bonin Trench, running through the Devil's Sea, reaches this depth. The conditions are so extreme that for most of scientific history, researchers believed that nothing could survive there. They were wrong, but the life that exists at Hadal depths is so different from surface life that it might as well belong to a different world. The first systematic surveys of the deep Pacific were undertaken in the late 19th century. The HMS Challenger expedition, which sailed from December of 1872 to May of 1876, was among the most ambitious scientific voyages in history. The vessel, a converted warship of the British Royal Navy, crossed every ocean, travelling nearly 70,000 nautical miles, and conducting deep-sea soundings at 362 stations. The depth measurements were taken using weighted hemp lines, lowered from the deck by hand, a process that could take hours for a single reading. The deeper the water, the longer the line and the longer the wait. The Challenger expedition revealed that the Pacific floor was far deeper and more varied than anyone had imagined. They discovered undersea mountains, vast abyssal plains of sediment, and trenches that plunged to previously unimaginable depths. They catalogued thousands of new species from the deep. They demonstrated that the ocean floor was not a featureless wasteland but a complex, dynamic environment with its own geology, its own biology, and its own rules. The expedition laid the foundation for the science of oceanography and transformed humanity's understanding of what lay beneath the surface of the sea. In the 20th century, technology advanced, and the surveys became more sophisticated. Echo sounders, which measure depth by timing the return of a sound pulse from the seabed, replaced the weighted lines of the Challenger era. These instruments could take continuous readings as a ship moved, building a profile of the seafloor along the ship's track. Later, multi-beam sonar systems were developed capable of mapping wide swaths of the seabed in a single pass. These tools revealed the true complexity of the Pacific floor in extraordinary detail, showing a landscape as varied as any on land. Mountain ranges, canyons, plateaus, volcanic cones, and trenches, all hidden beneath kilometers of dark water. The Japanese Hydrographic Association, the agency responsible for charting the waters around Japan, has classified the Devil's Sea region as requiring special navigational caution. This classification is not based on legends or superstitions. It is based on measured data, the documented instability of the seafloor, the ongoing volcanic activity beneath the surface, the magnetic anomalies caused by deposits of magnetized basaltic rock, the potential for sudden, unpredictable changes in water depth due to eruptions and seabed slumping. These are not possibilities. They are observed, documented, measured facts. Consider what all of this meant for a sailor in the mid-20th century, before satellite navigation existed. A ship enters the Devil's Sea, relying on a magnetic compass and dead reckoning, the time-honored method of tracking position by calculating speed and direction from a known starting point. The compass begins to drift because the volcanic rock beneath the water contains high concentrations of magnetite, pulling the needle away from magnetic north. The deviation is gradual, perhaps a degree or two over the span of an hour, barely noticeable without a second reference point. The navigator does not realize the error because nothing visible has changed. The ship drifts off course. Over hours, a 2-degree error compounds. The ship is now kilometers from where the navigator believes it to be. It sails over a previously uncharted seamount where volcanic gases are venting from the seabed. The water beneath the hull becomes less dense, saturated with carbon dioxide bubbles rising from a submarine eruption the crew cannot see or hear. The ship settles lower in the water, just slightly at first, and then if the eruption intensifies, if the gas plume thickens, the ship simply drops. No warning, no explosion, no storm, just silence, and then the ocean closing over the place where a vessel used to be, and a family waiting at a port for a ship that will never return. The scale of the Pacific makes any subsequent rescue or investigation nearly impossible. The Devil's Sea covers an area measured in hundreds of thousands of square kilometers. Searching this expanse for wreckage is not merely difficult. It is effectively impossible with conventional means. The currents in the Western Pacific, driven by the Kuroshio and its associated eddies, can carry floating debris thousands of kilometers from the site of a sinking within days. By the time a search begins, any wreckage that reached the surface, if any did, could be scattered across an area the size of a small country. And the wreckage that did not reach the surface, the hull, the cargo, the bodies, lies on a seabed that in many places is deeper than the height of the tallest mountains on land. Reaching it would require submersible technology that during the era of the disappearances simply did not exist. Then something happened that changed everything. The disappearances of the 1940s and 50s forced the Japanese government to confront a reality that no amount of tradition or experience had prepared them for. The ocean was not merely dangerous in the way that all oceans are dangerous, with storms and currents and hidden reefs. The Devil's Sea was dangerous in a way that was invisible, sudden, and total. Ships were vanishing without trace in calm weather, without sending distress calls, without leaving wreckage. The danger was coming from below, from the very seabed that the ships sailed over, and no one had any way to see it coming. The response was both practical and unprecedented. The Maritime Safety Agency issued formal warnings to all maritime traffic operating in the region. Charts were updated with caution zones. Shipping companies were advised to route their vessels around the most dangerous areas. And for a time, the flow of traffic through the Devil's Sea decreased, as captains who had heard the stories chose longer routes around the region rather than risk a direct crossing. But avoidance did not bring understanding, and without understanding, the danger remained, lurking beneath the surface, patient and unchanged. The volcanoes did not stop erupting because the ships stopped coming. The methane did not stop accumulating because the charts were revised. The tectonic plates did not pause their grinding collision because the government issued a warning. The Devil's Sea was not made safer by the warnings. It was merely made emptier. And an empty ocean tells you nothing about the dangers it contains. In the decades that followed, advances in technology began to peel back some of the layers of mystery. Satellite navigation systems, first developed for military use in the 1960s and made available to civilians in the 1980s and 90s, eliminated the problem of magnetic compass deviation. A ship equipped with a GPS receiver knows its position to within a few meters, regardless of the magnetic anomalies on the seabed below. This single technological advance probably saved more lives in the Devil's Sea than any scientific discovery, because it eliminated the navigational errors that had contributed to placing ships in the wrong location at the wrong time. Advances in sonar technology allowed more detailed mapping of the seabed. Multi-beam echo sounders, which emit a fan of sound pulses rather than a single beam, could map wide swaths of the ocean floor in a single pass, building three-dimensional models of the underwater topography with resolution measured in meters rather than the kilometers of earlier surveys. These instruments revealed the full complexity of the Devil's Sea floor, showing the seamounts, the trenches, the volcanic cones, and the fault lines in detail that was both beautiful and alarming. Satellite-based monitoring systems also improved the ability to detect submarine volcanic activity. Changes in sea surface temperature, detected by infrared sensors on orbiting satellites, can indicate the presence of a submarine eruption. Discoloration of the water caused by suspended volcanic particles can be spotted by optical sensors. These tools do not eliminate the danger, but they provide early warning that an eruption may be underway, allowing ships to be diverted away from the affected area. And yet, despite all of these advances, the Devil's Sea remains incompletely understood. The high-resolution mapping covers only a fraction of the region. Many seamounts have been detected but not surveyed in detail. The full extent of the methane hydrate deposits has not been determined. The volcanic monitoring systems are effective for detecting major eruptions, but may miss smaller events that are still capable of endangering a ship. The picture is clearer than it was in 1952, but it is far from complete. The fundamental challenge is one of scale. The Devil's Sea is enormous, and the hazards within it are dispersed across an area that would require years of continuous survey work to map comprehensively. Each survey expedition cost millions of dollars and places people and equipment in harm's way. The very act of studying the Devil's Sea is itself an exercise in risk management, as the researchers must operate in waters that have a documented history of destroying ships. There is a word that oceanographers use when discussing regions like the Devil's Sea. They call them undercharted. It is a polite way of saying that we do not know what is there. It is a polite way of saying that the maps have gaps, that the surveys are incomplete, that the next ship to cross a particular stretch of water will be sailing over territory that has never been properly examined. In most of the world's oceans, being undercharted is a minor concern. The seabed is stable, the water is predictable, and the risks are manageable. In the Devil's Sea, being undercharted is a different matter entirely. Because the seabed here is not stable, the water is not predictable, and the risks, as the crew of the Kaio Maru No. 5 learned, are not manageable by any technology or expertise that existed at the time, and perhaps not even by those that exist today. There is one final element of the Devil's Sea's physical character that must be understood before moving deeper into the mystery. The region sits squarely within what geologists call the Ring of Fire, the horseshoe-shaped belt of volcanic and seismic activity that encircles the Pacific Ocean. The Ring of Fire contains approximately 75% of the world's active and dormant volcanoes, and is responsible for roughly 90% of the world's earthquakes. It traces a path from the southern tip of South America up along the western coast of North America, across the Aleutian Islands of Alaska, down through Japan, and south through the Philippines, Indonesia, and New Zealand. At every point along this ring, tectonic plates are colliding, sliding past each other, or pulling apart, and at every point, the Earth responds with fire and tremor. Within this ring, the segment that includes the Devil's Sea is particularly active. The Izubonin-Mariana Arc, which defines the western and southern boundaries of the region, contains dozens of submarine volcanoes. Some erupt frequently, producing regular emissions of gas, pumice, and discolored water. Others have been quiet for decades or centuries, but show signatures of magma movement beneath the seabed, suggesting that they are not extinct, but merely sleeping. Seismic stations throughout the Western Pacific record thousands of earthquakes in this region every year. Most are small, detectable only by sensitive instruments, but each one is evidence of the ongoing tectonic processes that make the Devil's Sea what it is. A zone where the crust of the Earth is thinner, hotter, more fractured, and more prone to sudden, violent change than almost anywhere else on the planet. Adding to the volcanic and seismic hazards is a chemical one. The sediments along the margins of the deep trenches in the Devil's Sea contain vast deposits of methane hydrate, a crystalline substance in which methane gas is locked inside a cage of ice molecules under the immense pressure and low temperature of the deep seabed. These deposits are stable under normal conditions, but they are delicate. A shift in pressure caused by an earthquake, a rise in temperature caused by nearby volcanic activity, or even a change in the ocean current flowing over them can destabilize the ice structure and release the trapped methane in an explosive burst of gas. The methane rises through the water column, expanding as the pressure decreases, and when it reaches the surface, the water above has been transformed into a froth of liquid and gas that cannot support the weight of a ship. The existence of these deposits in the Devil's Sea has been confirmed by multiple surveys, and their potential to cause sudden, catastrophic loss of buoyancy is well established in the scientific literature. There is also the Kuroshio current to consider. This is one of the strongest ocean currents on Earth, the Pacific counterpart of the Gulf Stream in the Atlantic. The Kuroshio flows northeastward along the coast of Japan, carrying warm tropical water into the temperate Pacific at speeds that can exceed 2 meters per second. Where this powerful current encounters the seamounts, ridges, and trench walls of the Devil's Sea, it generates turbulence, eddies, and complex wave patterns that can be hazardous to shipping. The interaction of the Kuroshio with the undersea topography is one of the factors that makes the surface conditions in the Devil's Sea unpredictable, even when the weather overhead is calm. The practical consequence of all of this geology is simple and sobering. A vessel entering the Devil's Sea is entering a region where the ocean floor may shift beneath it, where the water may lose its ability to support a floating object, where the instruments may give false readings, and where the charts may be wrong, not because the charts were poorly made, but because the terrain they depict has changed since they were drawn. It is a region where the ordinary assumptions of maritime navigation, that the water will be deep enough, that the seabed will be where the chart says it is, that the compass will point north, are not reliable. And when those assumptions fail, in water this deep and this remote, the consequences are final. The ocean is patient. It has been patient for longer than humanity has sailed upon it. And the Devil's Sea, that particular stretch of patient, indifferent water, has been waiting in its way for as long as the plates beneath it have been moving, which is to say, far longer than there have been ships to swallow. But what scientists discovered next was worse than anyone expected. The core problem with the Devil's Sea is not that ships disappear there. Ships disappear all over the world's oceans, in storms, through mechanical failure, through human error, through piracy, through sheer bad luck. Maritime loss is a statistical certainty, a reality that the shipping industry has lived with for as long as ships have sailed. Roughly 2 to 3 large commercial vessels are lost every week somewhere in the world's oceans. These losses are tragic, but they are understood. They follow predictable patterns. They leave evidence. They can be investigated, explained, and in many cases, prevented through improvements in ship design, navigation, and safety procedures. The core problem with the Devil's Sea is different. It is the pattern of the disappearances, the speed with which they occur, and the total absence of evidence they leave behind. In most maritime disasters, something remains at the surface: a slick of fuel oil spreading across the waves, a scatter of debris, wooden planks, cargo containers, personal effects, a life jacket, inflated and empty, bobbing in the current, a body or several bodies floating face down, an empty life raft deployed by a crew that did not survive long enough to use it. In the worst cases, at least some wreckage is found, and from that wreckage, investigators can reconstruct what went wrong. In the Devil's Sea, during the peak period of disappearances in the mid-20th century, nothing remained. The ocean offered no clues, no oil slick, no debris field, no bodies, no life rafts, no floating wreckage of any kind. The ships were present, and then they were absent, and the ocean in between those two states offered no explanation whatsoever. It simply swallowed what it took and kept its silence, as if the ships had never existed at all. The recorded history of anomalous events in the Devil's Sea stretches back centuries. Japanese fishermen and coastal merchants have sailed the waters south of Tokyo for more than 1,000 years, and their oral traditions, passed down through generations in the fishing villages of the Izu and Bonin Island chains, contain references to ships that departed harbour and never returned. The stories speak of waters that churned and boiled without visible cause, of patches of ocean where the surface frothed and bubbled as if the sea were a pot of water set over a flame. They speak of strange sounds rising from the deep, low rumbles and groans that seem to come from the ocean floor itself. And they speak of a simple, practical warning that was repeated in every coastal village within sight of the Devil's Sea. Do not sail south when the water speaks. These accounts were long dismissed by outsiders as folklore, the kind of stories that every maritime culture develops to explain the ordinary dangers of the sea. Japanese culture, like many seafaring cultures, has a rich tradition of sea legends, stories of dragons and sea gods and supernatural forces that govern the behavior of the waves. It was easy for Western researchers to categorize the Devil's Sea legends alongside these mythological traditions and dismiss them as superstition. But the people who told those stories were not trying to create myths. They were trying to record observations. The boiling water was real. The rumbling sounds were real. The ships that failed to return were real. The fishermen were describing volcanic and seismic phenomena with the vocabulary available to them, and the fact that their vocabulary included references to devils and dragons did not make their observations any less accurate. The modern disappearances began in earnest during and after the Second World War. The exact timeline is disputed because wartime records were incomplete, and many vessel losses during the 1940s may have been caused by military action rather than natural hazards. But the post-war cases, occurring between 1945 and 1954, are well documented by the Japanese Maritime Safety Agency and cannot be attributed to combat operations. During this approximately 9-year period, at least 9 large vessels disappeared in the Devil's Sea region. The term large is relative, but in this context it refers to ships of substantial tonnage, ocean-going fishing trawlers, coastal cargo vessels, and at least one military patrol ship. These were not rowboats or canoes caught in rough water. They were seaworthy vessels crewed by experienced sailors who had spent their careers navigating the waters of the Western Pacific. They carried radio transmitters capable of sending distress signals. They carried flares, life rafts, and survival equipment. They had the means to call for help, and they did not call. They had the means to survive long enough for rescue, and no survivors were ever found. The pattern was consistent across the disappearances. Each ship entered the Devil's Sea region and was never heard from again. In most cases, the last reported position of the ship placed it within the boundaries of the zone as commonly defined. Weather records for the dates and locations of the disappearances show moderate or calm conditions in every case. No typhoons were present, no severe storms were recorded. The ships simply vanished in ordinary weather, in ordinary sea conditions, as if the ocean had opened beneath them and closed again. The case that transformed the Devil's Sea from a regional maritime concern into an international mystery was the loss of the Kaio Maru No. 5. This vessel was not a fishing boat or a cargo ship. It was a research vessel, a ship of approximately 190 tons, operated by the Japanese Maritime Safety Agency, specifically dispatched to investigate the previous disappearances. The decision to send the ship was itself remarkable. The Japanese government had concluded that the pattern of losses was serious enough to warrant a dedicated scientific investigation, and it committed resources and personnel to the mission. The Kaio Maru No. 5 carried a crew of 31, including scientists specializing in oceanography, geology, and meteorology, alongside the sailors needed to operate the vessel. It carried instruments for measuring water temperature, depth, and chemical composition. It carried magnetometers for surveying the local magnetic field. It carried seismographic equipment for detecting submarine earthquakes. It was, by the standards of 1952, well equipped for its mission. The ship departed in September of 1952 and entered the Devil's Sea to begin its survey. Communications with shore stations were maintained during the early portion of the voyage. The crew reported normal conditions, the instruments were functioning, the sea was calm. Then at some point during the survey, communications ceased. The radio fell silent. No distress call was received. No emergency frequency was activated. No flares were observed. The ship simply stopped communicating and, when search vessels were dispatched to the area, they found nothing. No wreckage at the surface, no oil, no debris. 31 human beings, gone, taken by the same waters they had been sent to study. The loss was devastating. The crew included some of Japan's most capable marine scientists, men who had devoted their careers to understanding the ocean. Their families waited at port for a ship that never returned. The government that had sent them was left to explain how it had lost the investigators it had dispatched to investigate the losses. The irony was bitter and impossible to ignore. The Devil's Sea had consumed the very effort to understand it. Later investigation, based on the ship's planned survey route and the known volcanic activity in the area at the time, led to the widely accepted conclusion that the Kaio Maru No. 5 was destroyed by a submarine eruption of Myojinsho. The volcano was in an active eruptive phase in September of 1952, and the ship's survey area overlapped with the volcano's location. The theory is that the vessel was operating near the volcano when a sudden eruption occurred beneath the surface, producing a shockwave through the water that either damaged the hull directly or, more likely, released a massive volume of gas that destroyed the buoyancy of the water around the ship, causing it to sink in seconds. This explanation is plausible. It is consistent with the known behavior of Myojinsho and with the physics of submarine volcanic eruptions. It explains the lack of a distress call, since the sinking would have been too rapid to allow communication. It explains the lack of surface wreckage, since the ship would have sunk intact rather than breaking apart. And it is supported by the later discovery of debris on the seafloor, in the area where the ship was believed to have been operating. But here is the problem. The Myojinsho hypothesis explains one disappearance. It does not explain 9. Not all of the vessels lost in the Devil's Sea were operating near Myojinsho. Some disappeared in areas far from any known active volcanic vent. The pattern of sudden, total disappearance was consistent across incidents separated by years and by hundreds of kilometers. If a single volcano were responsible, the disappearances would be expected to cluster around that volcano. They did not. They were spread across the entire Devil's Sea region. This distribution suggests that the cause, or causes, of the disappearances are not localized to a single feature, but are instead a property of the region as a whole. The Devil's Sea is not dangerous because of Myojinsho. Myojinsho is dangerous because it is in the Devil's Sea. The region's geology, its position above an active subduction zone, its network of volcanic vents and hydrothermal systems, its deposits of gas hydrates in the deep sediments, its complex magnetic field, all of these factors combine to create a zone where the conditions for sudden, catastrophic ship loss can arise at multiple points across a vast area. And it gets worse. The methane hydrate deposits in the Devil's Sea are not static, they are dynamic, responding to changes in temperature, pressure, and seismic activity. An earthquake in one part of the region can send pressure waves through the seabed that destabilize hydrate deposits kilometers away, triggering methane releases at locations that have no direct connection to the earthquake's epicenter. A volcanic eruption beneath the seafloor can heat the surrounding sediment, melting hydrate deposits over a wide area and producing gas releases that are dispersed across multiple sites. The Devil's Sea is not a collection of independent hazards. It is a system, and the system can produce effects that no individual hazard could produce on its own. The magnetic anomalies compound this danger in ways that are subtle but potentially fatal. Compass deviations in the Devil's Sea have been reported by sailors and pilots for decades. These deviations are caused by the magnetic properties of the volcanic rock that makes up the seabed, primarily basalt containing high concentrations of magnetite, one of the most strongly magnetic naturally occurring minerals. When large formations of this rock lie beneath the ocean, they create distortions in the Earth's magnetic field that can pull a compass needle away from true north. The deviations are not large, typically a few degrees, occasionally more. For a modern ship with GPS, they are irrelevant. For the ships of the 1940s and 50s, relying on magnetic compasses as their primary navigation tool, a few degrees of error sustained over hours of travel could place the vessel kilometers from its intended position. In the Devil's Sea, where the hazards are localized, being in the wrong position by even a few kilometers could mean the difference between safe passage and sailing directly over an active volcanic vent or an unstable methane deposit. There is also the question of rogue waves. The Devil's Sea lies in a region where the Kuroshio Current, one of the most powerful ocean currents on Earth, interacts with the complex undersea topography. When a fast-moving current flows over a seamount or along the edge of a trench, it generates turbulence that can produce waves far larger than the prevailing sea state would suggest. These rogue waves, defined as waves at least twice the significant wave height, can appear without warning in otherwise moderate conditions. In the Devil's Sea, rogue waves exceeding 15 to 20 meters have been estimated based on the known current speeds and topographic features. Though direct measurement in this region is sparse, a rogue wave alone is unlikely to sink a large ship without other contributing factors. But a rogue wave combined with reduced buoyancy from gas eruption, or structural damage from a seismic shockwave, or navigational error from a magnetic anomaly that placed the ship in the path of the wave rather than safely to one side, that combination could be fatal. And in the Devil's Sea, that combination is not unlikely. It is, given the geology and oceanography of the region, almost inevitable over time. The Japanese government responded to the disappearances with characteristic pragmatism. After the loss of the Kaio Maru No. 5, the Maritime Safety Agency issued formal navigational warnings, updated charts, and recommended that vessels avoid the most hazardous areas of the region. They did not claim to have solved the mystery. They simply acknowledged the danger and took practical steps to reduce exposure. In the years that followed, the disappearance rate in the Devil's Sea declined significantly. Whether this was because the warnings were effective, because volcanic activity decreased, or because the statistical clustering of losses in the 40s and 50s was partly coincidental, remains debated. What is not debated is the fundamental nature of the hazard. The Devil's Sea sits above an active tectonic boundary. Its volcanic systems are ongoing. Its methane deposits are real and measurable. Its magnetic anomalies are documented. And the combination of these factors creates a region where ships can be lost suddenly, completely, and without leaving evidence at the surface. This is not a theory. It is a description of a physical system whose components are individually well understood, but whose collective behavior remains incompletely characterized. Something is wrong with our assumptions about this place, not because the science is flawed, but because we have been studying the Devil's Sea as a collection of separate hazards rather than as an integrated system. Volcanism has been studied by volcanologists. Methane hydrates have been studied by geochemists. Magnetic anomalies have been studied by geophysicists. Rogue waves have been studied by oceanographers. Each field has produced valuable research, but no one has successfully modelled how all of these factors interact simultaneously in the Devil's Sea. And without that understanding, the central mystery remains. The recorded pattern of loss is consistent and unnerving in its regularity. Ship enters the region. Ship has radio contact. Ship reports normal conditions. Radio goes silent. Ship is never found. This sequence repeated itself multiple times over a period of roughly 14 years. No variation. No partial survival. No ship that made it partway through before sinking. The outcome was always the same. Total disappearance. Consider what this implies about the speed of the events involved. A large commercial vessel does not sink instantly under normal circumstances. Even in the worst maritime disasters, there is usually a period between the onset of the emergency and the final sinking, a period measured in minutes or hours during which the crew can attempt to save the ship, launch lifeboats, send radio signals, and deploy survival equipment. The sinking of the Titanic took 2 hours and 40 minutes from the initial collision with the iceberg to the ship's final plunge. The sinking of the Lusitania, torpedoed during the First World War, took 18 minutes. Even in cases of catastrophic structural failure, there is usually enough time for at least a partial distress call. In the Devil's Seas, no distress calls were received from any of the lost vessels. This is the single most important piece of evidence in the entire mystery, because it places a hard upper limit on the time between the onset of the emergency and the destruction of the ship. Sending a distress call on a marine radio takes seconds. The operator presses a key and speaks. If the ships in the Devil's Sea did not have time to do even this, the sinking must have occurred in a time frame measured in seconds, not minutes. The event, whatever it was, must have been virtually instantaneous, going from normal conditions to catastrophic loss in the time it takes to blink. There are very few natural phenomena capable of producing this kind of instantaneous effect on a ship at sea. A catastrophic gas eruption from the seabed is one of them. A direct hit from the shockwave of a submarine volcanic explosion is another. A combination of both, occurring simultaneously, is the most likely explanation. And in the Devil's Sea, where active volcanoes and methane hydrate deposits exist side by side above an unstable tectonic boundary, such a combination is not merely possible. It is, given enough time, virtually certain. The deeper investigation into the chemical properties of the Devil's Sea waters has revealed additional complexities. Water samples taken from areas near active submarine vents in the region show elevated levels of dissolved carbon dioxide, hydrogen sulfide, and in some cases methane. These gases are continuously seeping from the seabed through small fissures and vents that are too minor to cause buoyancy problems on their own, but that indicate the presence of much larger reservoirs of gas beneath the sediment surface. The seabed in the Devil's Sea is not solid in the way that a continental landmass is solid. It is porous, fractured, and laden with trapped gas that can be released by any disturbance significant enough to open the fractures wider. The analogy that researchers sometimes use is that of a carbonated beverage. The gas is dissolved in the liquid under pressure. As long as the container is sealed, the gas remains in solution. But if the seal is broken, if the pressure is suddenly released, the gas erupts from the liquid in a violent rush of bubbles. The seabed of the Devil's Sea is like a sealed container. The methane and carbon dioxide are trapped by the weight of the overlying sediment and water. But when an earthquake cracks the seal, or when a volcanic eruption melts the ice that holds the hydrates in place, the gas erupts. And the eruption, like the opening of a shaken bottle, can be sudden, violent, and impossible to predict from the surface. The cultural dimension of the Devil's Sea is also worth examining because it reveals something about the human relationship with unknown danger. The Japanese response to the disappearances was shaped by a culture that has a long and intimate relationship with natural disaster. Japan sits on the Pacific Ring of Fire, subject to earthquakes, tsunamis, volcanic eruptions, and typhoons. The Japanese concept of shizen, meaning nature but carrying connotations of inevitability and power, reflect an understanding that the natural world is not a passive backdrop to human activity, but an active force that must be respected and sometimes feared. The designation of the Devil's Sea as a danger zone was consistent with this cultural framework. The ocean was behaving in a way that was dangerous and not fully understood. The correct response was not to deny the danger or to challenge it, but to acknowledge it and adapt. This cultural response contrasts with the Western approach to the Devil's Sea, which has tended toward either sensationalism or dismissal. Western writers, particularly those in the tradition of Charles Berlitz and the Bermuda Triangle literature, seized upon the Devil's Sea as evidence of supernatural or extraterrestrial activity, weaving the disappearances into elaborate theories about ancient civilizations, underwater cities, and dimensional portals. These accounts sold millions of books but did nothing to advance understanding. At the other extreme, Western skeptics dismissed the Devil's Sea as a myth, arguing that the disappearances were neither unusual nor unexplained, merely the ordinary losses of a busy maritime region that had been inflated by sensational journalism. Both extremes missed the truth, which lies in the geology. The Devil's Sea is not supernatural, and it is not ordinary. It is a geologically extraordinary region where real, measurable, physical hazards combine to create conditions that are genuinely more dangerous than the surrounding ocean. The disappearances are not evidence of dragons or aliens. They are evidence of volcanic eruptions, methane releases, magnetic anomalies, and seismic events occurring in combination in a region that happens to be poorly charted and far from rescue resources. The explanation is natural. That does not make it less disturbing. If anything, a natural explanation is more disturbing than a supernatural one because a natural cause can happen again. Something is wrong with our assumptions about this place, not because the science is flawed, but because we have been studying the Devil's Sea as a collection of separate hazards rather than as an integrated system. Volcanism has been studied by volcanologists. Methane hydrates have been studied by geochemists. Magnetic anomalies have been studied by geophysicists. Rogue waves have been studied by oceanographers. Each field has produced valuable research, but no one has successfully modelled how all of these factors interact simultaneously in the Devil's Sea. And without that integrated understanding, the central mystery remains unresolved. But here is what makes this truly terrifying. The investigation of the Devil's Sea's chemical properties has extended beyond the immediate vicinity of known volcanic features. Surveys conducted by Japanese oceanographic vessels in the 1990s and early 2000s deployed water sampling arrays across a broad grid covering the entire region. These arrays collected water at multiple depths, from the surface down to the thermocline and beyond, measuring dissolved gas concentrations, temperature, salinity, and pH. The findings painted a picture of an ocean that was chemically distinct from the surrounding Pacific in subtle but significant ways. Dissolved carbon dioxide levels in the Devil's Sea were consistently higher than in adjacent waters of similar depth and temperature. The excess was not dramatic, not the kind of difference that would be immediately obvious to a chemist running a single test, but it was persistent and widespread, present in samples taken at every station across the survey grid. This elevated carbon dioxide was not coming from the atmosphere. Atmospheric carbon dioxide dissolves into the ocean surface at a rate determined by temperature and wind conditions, and those conditions were similar across the entire survey area. The extra carbon dioxide was coming from below, seeping upward from the volcanic and hydrothermal systems embedded in the seabed. The implications of this chronic degassing are important and have been underappreciated. A persistent background flux of carbon dioxide from the seabed means that the water column in the Devil's Sea is, in a sense, pre-charged. It is already carrying a higher load of dissolved gas than normal ocean water. This matters because the solubility of a gas in water depends on pressure and temperature. At depth, where the pressure is high, water can hold large amounts of dissolved gas in stable solution. But as water moves upward, whether carried by currents or forced upward by an eruption, the pressure decreases and the water's capacity to hold gas in solution diminishes. If the water is already close to saturation, Even a modest reduction in pressure can cause the gas to come out of solution as bubbles. In the Devil's Sea, where the background gas load is elevated, the threshold for spontaneous bubble formation is lower than in normal ocean water. This means that the safety margin for ships transiting the region is thinner than it would be elsewhere. A seismic disturbance that would produce only a minor, harmless release of gas in a normal ocean could, in the pre-charged waters of the Devil's Sea, trigger a cascade of bubble formation that erates a significant volume of water near the surface. The individual perturbation need not be dramatic. The background conditions amplify its effect. It is the difference between lighting a match in a room full of fresh air and lighting a match in a room where gas has been slowly leaking for hours. The match is the same. The consequence is not. Hydrogen sulfide, a toxic gas produced by volcanic and hydrothermal activity, was also found at elevated levels in deep water samples from the Devil's Sea. Hydrogen sulfide is deadly to humans at concentrations well below those required to produce a detectable odor in the atmosphere. In solution in seawater, it poses no direct threat to ships, but its presence is a tracer, an indicator of active subsurface degassing that also involves other more dangerous gases. Where hydrogen sulfide is found, methane and carbon dioxide are likely present as well, and the concentrations measured in the Devil's Sea confirm this correlation. The deep water in the region carries a chemical signature of active geological processes, a fingerprint of the volcanism and tectonic strain that characterize the seabed below. The thermal structure of the water column in the Devil's Sea also departs from the regional norm. Hydrothermal venting from the seabed injects heat into the deep water, creating thermal anomalies, pockets of warmer water at depth that can persist for weeks or months before dissipating into the surrounding ocean. These thermal anomalies are not dangerous in themselves, but they affect the behavior of dissolved gases. Warmer water holds less gas in solution than cooler water at the same pressure. A thermal anomaly can therefore act as a gas concentrator, driving dissolved methane and carbon dioxide out of the water and into bubble phase even without a sudden pressure change. In the Devil's Sea, where both elevated gas concentrations and thermal anomalies exist simultaneously, the interaction between the two creates conditions that are more volatile than either factor alone would produce. The physical oceanography of the region adds yet another layer of complexity. The Kuroshio Current does not flow smoothly through the Devil's Sea. It meanders, forming large-scale undulations that shift position over time. Where the current bends, it creates eddies, rotating masses of water that can be hundreds of kilometers in diameter and can persist for months. These eddies trap water within their circulation, effectively isolating it from the surrounding ocean. Water trapped in a warm core eddy, where the current encloses a mass of warm tropical water, can carry different chemical and thermal properties from the water just outside the eddy boundary. If an eddy forms over a region of active degassing, the gas released from the seabed accumulates within the eddy's trapped water, building up to concentrations that would normally be dispersed by the current. The eddy acts as a container, holding the gas in place until some disturbance, a storm, a current shift, a seismic event, releases it all at once. This eddy trapping mechanism is speculative, and no study has definitively linked it to any specific ship disappearance. But the physics is sound. Eddies in the Kuroshio system are well documented. Degassing from the seabed of the Devil's Sea is well documented. The combination of the two is not merely possible but, given the geography and oceanography of the region, probable. It represents another way in which the Devil's Sea's hazards are not independent but are linked, coupled by the physical dynamics of the ocean in ways that are difficult to predict and almost impossible to observe in real time. The temporal dimension of the disappearances also deserves closer examination. The clustering of losses between approximately 1940 and 1954 has been noted by every serious researcher who has examined the data. Some have attributed this clustering to statistical coincidence, arguing that in a region with heavy maritime traffic, a random distribution of losses will occasionally produce clusters that appear significant but are not. Others have argued that the clustering reflects a real increase in hazard during that period. perhaps linked to a phase of heightened volcanic or seismic activity along the Izu-Bonin Arc. The geological record supports the second interpretation, at least partially. The period from the late 1940s through the early 1950s was marked by a notable increase in volcanic activity along the Izu-Bonin chain. Myojincho erupted repeatedly during this period, with major events in 1952 and 1953. Other volcanic features in the region also showed increased activity. Earthquakes along the subduction zone were frequent. The geological evidence suggests that the tectonic stress in the region was elevated during this period, producing a surge of volcanic and seismic activity that would have increased the danger to shipping. If this interpretation is correct, it suggests that the Devil's Sea may have cycles of heightened danger, periods when the tectonic stress builds to a level that produces increased volcanism, seismicity, and gas release, followed by periods of relative quiescence when the stress has been partially relieved. The historical record is too short and too incomplete to confirm this cyclical pattern with confidence, but the hypothesis is consistent with what we know about how subduction zones behave. Tectonic stress accumulates slowly over decades and is released in bursts of activity that can last years or decades before subsiding. If the Devil's Sea operates on such a cycle, then the period of peak disappearances may represent a peak of geological activity, and the apparent safety of the region in subsequent decades may represent a trough, a temporary respite, not a permanent resolution. This possibility is, in its quiet way, profoundly unsettling. It means that the Devil's Sea's period of greatest danger may not be behind us. It may be ahead. The tectonic forces that produced the surge of activity in the 1940s and 50s have not ceased. The Philippine Sea Plate is still diving beneath the Eurasian Plate at the same rate. The stress is still accumulating. The volcanoes are still connected to the same magma sources. The methane is still accumulating in the sediments. If the cycle repeats, and geological cycles always repeat, then there will come a time when the Devil's Sea becomes, once again, as dangerous as it was in its worst years. The only question is when. And to that question, the current state of our knowledge offers no answer. But here is what makes this truly terrifying. The history of humanity's attempts to understand the Devil's Sea is a story of incremental progress and persistent failure. Not because the investigators lacked intelligence or resources, but because the ocean itself resists investigation with a thoroughness that is difficult to overstate. Every expedition into the Devil's Sea has revealed new information. Every survey has added detail to the map. But every advance in knowledge has also deepened the mystery, revealing new layers of complexity that were not previously suspected. The Devil's Sea does not yield its secrets easily, and what it does reveal is often more disturbing than what it conceals. The first major systematic study of the region was conducted by the Japanese Maritime Safety Agency in the years following the disappearances. Beginning in the mid-1950s, the agency undertook a series of bathymetric surveys using echo sounders to map the depth and contours of the seabed throughout the Devil's Sea region. The surveys also employed magnetometers, instruments that measure the strength and direction of the local magnetic field, to identify areas where magnetic anomalies might interfere with compass navigation. The work was dangerous. The surveyors were operating in the same waters that had destroyed the Kaio Maru No. 5, and they knew it. They proceeded with extreme caution, maintaining safe distances from known volcanic features and monitoring their instruments continuously for signs of seismic activity. The methodology itself was painstaking. Echo sounders of the era operated by emitting a pulse of sound from a transducer mounted on the hull of the survey vessel, then measuring the time it took for the echo to return from the seabed. The depth was calculated from the speed of sound in water and the round-trip travel time. Each measurement gave a single depth reading at a single point beneath the ship. To map the seabed over a large area, the vessel had to transit back and forth in a grid pattern, taking readings at regular intervals, slowly building up a picture of the underwater terrain line by line. In the Devil's Sea, where depths routinely exceeded several thousand meters, and where the bottom topography was extremely irregular, this process was slow, expensive, and incomplete. The survey lines could capture the broad features of the seabed, the trenches, the seamount chains, the ridges, but they inevitably missed features that fell between the lines. A volcanic cone a few hundred meters in diameter could easily escape detection if the survey line passed to either side of it. The results were sobering. The surveys revealed a seafloor that was far more complex and hazardous than previous charts had indicated. The region was studded with seamounts, many of them previously uncharted, rising from the deep trench floors to heights of several thousand meters. Some came within a few hundred meters of the surface. Between these seamounts lay deep valleys and basins, some of them showing signs of recent volcanic activity. Fresh lava flows, deposits of pumice, and fields of hydrothermal vents releasing superheated water and dissolved minerals from the interior of the Earth. But the most alarming finding was the instability. Features that had been mapped during one survey were absent during the next. Seamounts that had been recorded at one depth were found at a different depth months later, sometimes shallower, sometimes deeper, as if the seabed itself were breathing. In some cases, entirely new features appeared where none had been charted before. A seamount might rise from the seafloor in the interval between two surveys, a volcanic cone that simply had not existed the previous year. This meant that nautical charts of the Devil's Sea had a limited shelf life. A chart that was accurate when published could become dangerously misleading within months or years, as the seabed beneath the charted waters continued to reshape itself. The implications for navigation were profound. A ship relying on a chart published even a few years earlier might encounter features the chart did not show. Worse, it might fail to find features the chart did show because they had been buried or reshaped by volcanic activity. In an era before real-time sonar and satellite monitoring, a ship entering the Devil's Sea was essentially navigating by outdated information, trusting a map of a landscape that was no longer the same landscape. This problem has not been fully resolved even today. While modern multi-beam sonar can map the seabed with far greater resolution than the echo sounders of the 1950s, comprehensive surveys of the Devil's Sea region are infrequent and the seafloor continues to change between surveys. The map is always behind the territory. The second major angle of investigation focused on the submarine volcano Myojinsho, which had become the prime suspect in the disappearance of the Kaio Maru No. 5. Japanese volcanologists established a monitoring program for Myojinsho in the 1950s that has continued, with various interruptions and upgrades, to the present day. Seismographs were placed on nearby islands to detect the tremors that precede and accompany volcanic eruptions. Hydrophones, underwater microphones, were deployed in the surrounding waters to listen for the characteristic sounds of submarine eruptions. Deep, low-frequency rumbles that travel enormous distances through the water. Over the decades, this monitoring program has documented dozens of eruptions of Myojinsho. The eruptions range in intensity from minor events that produce small amounts of pumice floating at the surface, sometimes reported by passing ships as mysterious patches of discolored water, to major explosive events that generate underwater shockwaves detectable hundreds of kilometers away. In 1952, a series of major eruptions created a temporary island that rose approximately 100 meters above sea level before being eroded and reabsorbed by the ocean within weeks. In 1960, another eruption produced a significant pumice raft, a floating mass of volcanic rock that drifted across the Pacific for months before dispersing. These pumice rafts themselves pose a navigational hazard. A large raft of pumice can clog engine cooling intakes, foul propellers, and reduce hull speed. For a small vessel with limited reserves of fuel and water, becoming trapped in a pumice field could be a life-threatening event even without the direct danger of the eruption that produced it. The monitoring also revealed something important about the nature of submarine eruptions. On land, a volcanic eruption gives warning signs. The ground shakes. Gases vent from fissures. The mountain visibly deforms as magma pushes upward from below. There is time, usually, to detect the signs and issue warnings. Beneath the ocean, the situation is entirely different. The weight of the overlying water suppresses many of the precursors that would be visible on land. An eruption can begin and reach full intensity before any sign appears at the surface. A ship passing over a submarine volcano might have no indication whatsoever that an eruption is underway until the effects reach the hull, and by then it is far too late. The physics of submarine volcanic explosions deserves detailed consideration because it explains the speed and completeness of the disappearances. When a volcanic explosion occurs beneath the ocean, the energy is transmitted primarily as a pressure wave through the surrounding water. Water is nearly incompressible, which means that it transmits pressure waves extremely efficiently, far more efficiently than air. The shock wave from a moderate submarine eruption of Myojincho was estimated by Japanese researchers to release energy equivalent to several kilotons of explosive force, comparable to a small nuclear detonation. This shock wave travels through the water at over 1,500 meters per second, reaching a ship on the surface in seconds, regardless of its distance from the vent. The effect of this shock wave on a ship's hull depends on the energy of the wave and the distance from the source. At close range, within a few hundred meters of the eruption, the shock wave can rupture the hull plates of a steel vessel, producing catastrophic flooding that sinks the ship within seconds. At greater distances, the shock wave may not rupture the hull but can cause severe structural damage, buckling frames, springing rivets, cracking welds, and opening seams that allow progressive flooding. In combination with the gas release that accompanies the eruption, which creates a zone of reduced buoyancy at the surface, even moderate hull damage can be fatal. The ship begins to take on water through the damaged hull, at the same time that the water around it loses the ability to provide full buoyancy support. The result is a sinking that is both rapid and total. The gas release that accompanies the eruption can aerate thousands of cubic meters of water, creating a zone of reduced buoyancy that extends across an area larger than several football fields. Any ship within this zone faces catastrophic danger, and the zone is invisible from the surface until the moment it forms. 1 second, the water is supporting the ship normally. The next, it is not. The transition is instantaneous, and the ship's response, dropping bodily into the aerated water, is equally instantaneous. There is no gradual sinking, no listing, no opportunity to react. The deck drops beneath the crew's feet, and the ocean closes over the vessel before a hand can reach the radio. The third angle of investigation explored the methane hydrate hypothesis in greater detail. In the 1990s and 2000s, advances in deep-sea survey technology, particularly remotely operated vehicles and high-resolution side-scan sonar, allowed researchers to map the distribution of gas hydrate deposits on the seabed of the Devil's Sea region with unprecedented precision. The results confirmed that significant deposits of methane hydrate exist along the margins of the Izu-Bonin Trench and in sediment basins between volcanic features. These deposits contain enormous quantities of methane, locked in ice at the seabed under high pressure and low temperature. The structure of methane hydrate is worth understanding because it determines how the material behaves when disturbed. Methane hydrate is a clathrate compound, a crystalline lattice of water molecules that traps methane molecules within its structure. The result looks like ordinary ice but behaves differently. When ignited, it burns because the trapped methane escapes and combusts, a property that has earned it the nickname fire ice. More importantly for the Devil's Sea, methane hydrate is stable only within a narrow range of temperature and pressure conditions. Below a certain temperature and above a certain pressure, the hydrate is solid and inert. But if the temperature rises or the pressure drops beyond the stability threshold, the hydrate disintegrates, releasing the trapped methane as a burst of free gas. This disintegration can be triggered by a variety of geological events. An earthquake can fracture the sediment that confines the hydrate, reducing the pressure on the deposit. A volcanic eruption can heat the surrounding sediment, raising the temperature. A landslide on an underwater slope can remove the overlying material that provides the necessary pressure. Any of these triggers can initiate a rapid release of methane from a hydrate deposit. Researchers at the University of Sunderland in the United Kingdom conducted a series of landmark studies in the early 2000s, examining the mechanics of methane-induced ship sinking. They built laboratory models that simulated the release of gas from the seafloor beneath the model ship. In every trial, the result was the same. When the gas was released, the water above the source became aerated. The model ship, which had been floating stably moments before, lost buoyancy and sank vertically. The sinking was rapid, occurring in 2 to 3 seconds in laboratory conditions. The ship did not capsize. It did not break apart. It simply dropped, as if a trapdoor had opened beneath it. The researchers calculated that a natural methane eruption of sufficient magnitude could produce the same effect on a full-sized vessel, sinking it so quickly that the crew would have no time to respond. The Sunderland experiments were compelling, but also identified important limitations. The laboratory conditions were controlled and idealized. In the open ocean, the picture is more complicated. Ocean currents can disperse a gas plume before it reaches the surface, diluting its effect. The depth of the water matters enormously. In shallow water, a relatively small gas release can produce a lethal effect at the surface because the gas does not have far to travel and does not disperse significantly during its ascent. In deep water, the gas must rise through thousands of meters, expanding and dispersing as it goes, and the surface effect may be greatly reduced or eliminated entirely. Whether the methane deposits in the Devil's Sea are capable of producing eruptions large enough and rapid enough to sink a ship in deep water remains an open question. The physics supports the possibility. The direct evidence is insufficient to confirm it. The fourth angle of investigation examined the role of the Kuroshio current and its interaction with the undersea topography. The Kuroshio is one of the great western boundary currents, the Pacific counterpart of the Gulf Stream in the Atlantic. It flows northeastward along the coast of Japan at speeds that can exceed 2 meters per second, carrying warm tropical water into the temperate Pacific. Where the Kuroshio passes over the seamounts and trench margins of the Devil's Sea, it generates complex hydrodynamic effects, eddies, standing waves, zones of convergence where opposing currents collide, and areas of intense turbulence where water is forced over and around underwater obstacles. These effects are not merely theoretical. They have been measured by oceanographic buoys and by ships transiting the region. Sailors have reported sudden, unexpected changes in sea state while crossing the Devil's Sea. Encounters with steep, confused waves that seem to come from nowhere, patches of water where the surface churned and broke for no apparent reason. Some of these reports may be exaggerated, but the physical basis for them is well established. When a fast-moving current flows over an abrupt change in bottom depth, such as the flank of a seamount, the water is forced upward and then drops rapidly on the downstream side, creating a zone of intense turbulence that can extend to the surface. The waves generated by this process are not wind-driven and do not follow the patterns that sailors use to anticipate sea conditions. They appear suddenly, without the build-up of swell that normally precedes heavy seas, and they can be steep enough to break, sending tons of water crashing across the deck of an unprepared vessel. When the Kuroshio interacts with tidal currents in the region, the effects intensify further. Tidal currents in the Western Pacific are driven by the gravitational pull of the Moon and the Sun, and they oscillate roughly twice daily. When a tidal current opposes the flow of the Kuroshio, the resulting friction generates steep, short-period waves with heights disproportionate to the wind conditions. These waves are difficult to predict and difficult to navigate, and they have been responsible for maritime incidents throughout the waters around Japan. In the Devil's Sea, where the bottom topography is more extreme than in most coastal waters, the combination of the Kuroshio and tidal currents can produce sea conditions that are genuinely hazardous to even large, well-built vessels. A fifth and more controversial angle of investigation has focused on electromagnetic anomalies. The Devil's Sea has long been associated with reports of instrument malfunctions. Pilots flying over the region have reported compass deviations, radio interference, fluctuations in altimeter readings, and temporary failures of electronic equipment. These reports are anecdotal and difficult to verify scientifically. Many come from military personnel during the Cold War era, when the Western Pacific was heavily patrolled by both American and Japanese forces, and the reliability of such reports under wartime security constraints is uncertain. However, the physical basis for electromagnetic anomalies in the Devil's Sea is well established. The seabed in this region is composed largely of basaltic volcanic rock, which contains high concentrations of magnetite and other magnetic minerals. When large formations of this rock lie beneath the surface, they create local distortions in the Earth's magnetic field that are measurable by magnetometer and have been documented by multiple Japanese surveys. The distortions are localized, strongest directly above the most magnetic features, and they diminish rapidly with distance. Whether they are powerful enough to affect aircraft instruments at cruising altitude is debatable. That they can affect maritime compasses at the surface is not debatable. It has been measured and confirmed repeatedly over decades of surveys. The Japanese researcher Shigemi Ataya published a study correlating reported navigational anomalies with the locations of known magnetic features on the seabed. The correlation was statistically significant. Ships and aircraft that reported compass deviations were disproportionately likely to have been transiting areas where strong magnetic anomalies existed. This did not prove causation, as a ship that drifts off course due to any cause is more likely to be reported as a navigational anomaly regardless of the specific cause. But the pattern was suggestive, and it added another piece to the increasingly complex puzzle of the Devil's Sea. Beyond these 5 major angles of scientific investigation, there are peripheral contributions that deserve mention. In the 1970s, the writer Charles Berlitz, who had previously popularized the Bermuda Triangle mystery, turned his attention to the Devil's Sea. His book, The Dragon's Triangle, published in 1989, compiled accounts of disappearances, strange phenomena, and unexplained events in the region. Berlitz was a skilled storyteller but a careless researcher, and his work was criticized for exaggeration, inaccuracy, and a failure to distinguish between documented events and unverified claims. Some of the incidents he attributed to the Devil's Sea may have occurred outside the region entirely. Others may not have occurred at all. His contribution to public awareness was significant, but his contribution to scientific understanding was negligible, and in some respects actively harmful, as it associated serious research on the region with sensationalism and pseudoscience. The skeptic Larry Couchet, who had previously debunked many of the claims about the Bermuda Triangle, also examined the Devil's Sea legend. Couchet argued that the disappearance rate in the Devil's Sea was not statistically unusual for a region of its size in a heavily trafficked ocean. He pointed out that the Western Pacific is one of the most typhoon-prone areas on Earth, and that many of the disappearances attributed to mysterious forces could be explained by storms, mechanical failures, and the ordinary dangers of open ocean navigation. Couchet's analysis was rigorous and methodologically sound, and it made valid points about the tendency of popular accounts to inflate the mystery. But it also had important limitations. He was working primarily from published English-language sources and may not have had access to the full range of Japanese-language records documenting the disappearances. His statistical analysis, while correct on its own terms, did not account for the specific characteristics of the losses, particularly the absence of distress calls and wreckage, which distinguish the Devil's Sea disappearances from ordinary maritime losses. The truth, as is often the case, lies somewhere between the sensationalism of Berlitz and the skepticism of Couchet. The Devil's Sea is not the supernatural death trap depicted in popular culture, but neither is it an ordinary stretch of ocean whose dangers have been exaggerated by myth and repetition. The documented loss of the Kaio Maru No. 5 is real. The volcanic activity is real. The methane deposits are real. The magnetic anomalies are real. And the pattern of sudden, complete disappearances, while perhaps not as statistically extraordinary as the legends suggest, is consistent with the known hazards of the region in ways that ordinary storms and mechanical failures cannot fully explain. What is most sobering about the collective body of research on the Devil's Sea is not what it has explained, but what it has failed to explain. Each individual hypothesis, volcanism, methane, seismicity, magnetic anomalies, rogue waves, hydrodynamic effects, accounts for some of the observed phenomena. None accounts for all of them, and no study has yet successfully modeled how these hazards interact as a system. The Devil's Sea may be dangerous precisely because its hazards are not independent. They may be coupled linked by the underlying geology in ways that produce effects far more dangerous than any single hazard in isolation. A seismic event might trigger a volcanic eruption. A volcanic eruption might destabilize a methane hydrate deposit. A methane eruption might coincide with a rogue wave generated by the Kuroshio current passing over a seamount. A magnetic anomaly might have nudged the ship off course hours earlier, placing it over the epicenter of the event rather than safely to one side. Each link in this chain is physically plausible. Each has been observed or modeled independently. But the full chain, from initial trigger to final sinking, has never been directly observed, because observing it would require being in exactly the wrong place at exactly the wrong time. And the defining characteristic of the Devil's Sea is that those who find themselves in the wrong place at the wrong time do not return to report what they witnessed. This is the fundamental challenge. The Devil's Sea is a system that can only be fully understood by observing it in its most dangerous state, and observing it in that state is precisely what the system does not allow. The scientists aboard the Kaio Maru No. 5 learned this truth at the cost of their lives. They went to observe. The ocean did not cooperate. It never does. The deeper truth about the Devil's Sea is not about the Devil's Sea at all. It is about what the Devil's Sea reveals, about our relationship with the planet we inhabit. We speak of Earth as if we know it. We have mapped its continents, surveyed its mountain ranges, charted its rivers and deserts. We have sent satellites into orbit that photograph every square meter of the surface, in visible, infrared, and radar wavelengths. We carry devices in our pockets that can pinpoint our location to within a few meters anywhere on land. And yet, beneath the surface of our oceans, the Earth remains almost entirely unknown. The statistic is repeated so often that it has lost its power to shock, but it should not lose that power, because it is true and it is staggering. According to the National Oceanic and Atmospheric Administration, more than 80% of the ocean floor has never been observed, mapped, or explored by any human instrument. Some estimates place the figure even higher, at 95% when measured against the standard of high-resolution bathymetric mapping. We have better maps of the surface of Mars, a planet more than 55 million kilometers away at its closest approach, than we do of the bottom of our own ocean. Let that sink in. We have walked on the surface of the Moon. 12 people have stood on lunar soil and looked back at the Earth from a distance of nearly 400,000 kilometers. We have driven robotic vehicles across the surface of Mars, drilling into its rocks and analyzing its atmosphere. We have sent probes to the moons of Jupiter and Saturn, captured images of Pluto from close range, and pushed spacecraft beyond the boundary of our solar system into interstellar space. These are extraordinary achievements. They represent the very best of human curiosity and human engineering, and yet the deepest point in our own ocean was not reached by a human being until January of 1960, when the Swiss engineer Jacques Piccard and the American naval officer Don Walsh descended to the bottom of the Challenger Deep in the bathyscaphe Trieste. They reached a depth of approximately 10,916 meters. The dive took nearly 5 hours. They spent only about 20 minutes at the bottom, peering through a small viewport at a world no human had ever seen. The sediment stirred up by their landing obscured most of the view. They saw a flat, featureless floor of pale sediment, dimly illuminated by the Trieste's external lights. A flatfish, possibly a sole, was observed resting on the bottom, proof that vertebrate life could exist at the greatest depths. Then they began their ascent. Since that dive, fewer than 24 people have reached the Hadal Zone, the deepest layer of the ocean below 6,000 meters. More people have walked on the Moon. The disparity between our investment in space exploration and our investment in ocean exploration is not merely a curiosity of funding priorities. It reflects something deeper about human psychology. Space is dramatic. It is visually spectacular, with its galaxies and nebulae and planetary surfaces bathed in alien light. It lends itself to narrative and to heroism. The ocean is the opposite. It is dark, cold, and crushingly heavy. It does not photograph well. There are no panoramic vistas at the bottom of a trench, only mud and darkness, and the occasional creature that looks like it belongs in a nightmare. Space exploration produces images that inspire wonder. Deep ocean exploration produces images that inspire unease. We fund accordingly. The consequences of this disparity are not merely academic, they are practical and urgent. The ocean floor contains resources, geological hazards, and biological communities that are directly relevant to human survival and prosperity. Mineral deposits on the seabed contain concentrations of rare metals that are essential for modern electronics and renewable energy technologies. Geological processes on the ocean floor, volcanic eruptions, earthquakes, methane releases, produce hazards that threaten coastal communities, shipping lanes, and undersea infrastructure, including the fiber optic cables that carry more than 95% of intercontinental data traffic. Biological communities in the deep sea may contain organisms that produce novel compounds with pharmaceutical or industrial applications. We are ignoring all of this because the deep ocean is dark, inaccessible, and uncharismatic. The Devil's Sea sits above geology that connects to this unexplored world. The Izubonin Trench, running through the region, descends to depths exceeding 9,700 meters. At these depths, conditions are so extreme that they defy casual comprehension. The pressure at the bottom of the trench exceeds 1,000 atmospheres, meaning that every square centimeter of surface area bears a weight equivalent to 1,000 kilograms. A human body at this depth would be compressed to a fraction of its normal volume. A steel vessel, unless specifically engineered to withstand the pressure, would be crushed like an aluminum can under a boot. The temperature hovers near freezing, typically between 1 and 4 degrees Celsius, though hydrothermal vents can create localized zones of extreme heat. There is no light. The sun's rays, even at their most penetrating, are absorbed within the first few hundred meters of the water column. Below that, the ocean is in a state of permanent midnight that has persisted since the trenches first formed tens of millions of years ago. And yet, life exists there. Creatures have been found in the Hadal Zone that challenge our understanding of what is biologically possible. Amphipods, small crustaceans related to shrimp, have been collected from depths exceeding 10,000 meters, their bodies specially adapted to the crushing pressure through biochemical modifications to their cell membranes that maintain flexibility under conditions that would solidify the membranes of surface organisms. Xenophyrophores, giant single-celled organisms the size of tennis balls, carpet the floors of deep trenches, feeding on organic particles that drift down from the productive surface waters thousands of meters above. Snailfish have been filmed at depths exceeding 8,000 meters, their bodies translucent and ghostly, their bones partially dissolved by the chemical conditions of the deep water, adapted to an environment that would kill any surface fish within seconds. The most remarkable deep-sea communities are those that have abandoned sunlight entirely as an energy source. Around hydrothermal vents, where superheated water laden with dissolved minerals erupts from the seabed at temperatures exceeding 300 degrees Celsius, entire ecosystems thrive on chemosynthesis rather than photosynthesis. Bacteria at the base of these food chains harvest chemical energy from the hydrogen sulfide and other compounds dissolved in the vent fluids, using this energy to fix carbon in the same way that surface plants use sunlight. These bacteria support communities of tube worms, clams, mussels, shrimp and crabs that cluster around the vents in densities that rival tropical coral reefs. The tube worms, in particular, are remarkable. Some species grow to lengths exceeding 2 meters, their bodies enclosed in white tubes anchored to the rock, their red plumes of gills extending into the warm vent fluid to absorb the chemicals that sustain them. They have no mouth, no stomach, no digestive tract. They are sustained entirely by symbiotic bacteria living within their tissues, bacteria that convert hydrogen sulfide into organic molecules that nourish the worm. This is not science fiction. This is the documented reality of the deep ocean, confirmed by submersible expeditions and remotely operated vehicle surveys conducted by research institutions in Japan, the United States, the United Kingdom, and other nations over the past several decades. The deep sea contains ecosystems that operate on entirely different principles from the surface world. They exist in complete independence from sunlight. They are powered by the internal heat and chemistry of the Earth itself, drawing energy from the same geological forces that make the Devil's Sea dangerous to ships. The relevance is direct and unsettling. The volcanic and hydrothermal activity that endangers vessels at the surface is the same activity that sustains life at the bottom. The forces that swallow ships are the forces that feed ecosystems. The Devil's Sea is not a dead zone. It is, paradoxically, one of the most biologically active regions of the deep ocean, teeming with organisms that have never seen the sun and never will, thriving in conditions that would kill any surface creature instantly. The surface of the Devil's Sea may appear empty and hostile, a flat expanse of grey water under a grey sky, but beneath that surface, the ocean is alive with a violence and a vitality that the surface world cannot match. There is an irony here that is worth pausing to appreciate. We fear the Devil's Sea because it kills, but the same processes that make it deadly to us are the processes that give it life. The volcanic eruptions that can destroy a ship in seconds also create the hydrothermal vents that sustain some of the most exotic biological communities on Earth. The methane that erupts from the seabed and sinks vessels also feeds communities of methane-oxidizing bacteria that form the base of cold seep ecosystems, another type of deep-sea community that exists independently of sunlight. The tectonic forces that make the region unstable and unpredictable are the same forces that have been building new ocean floor for millions of years, creating habitat, generating chemical gradients, and sustaining biological diversity in the perpetual darkness of the deep. The deeper truth is that we are afraid of the wrong things. We fear the unknown, and rightly so. The Devil's Sea has taken lives and destroyed ships, and it deserves caution and respect. But the greater fear should be directed not at what the Devil's Sea has done, but at what it represents. The vast, overwhelming ignorance that characterizes our relationship with the ocean. We are a species that has mastered the surface of its planet. We have built cities that rise 100 stories into the air. We have dammed rivers and diverted lakes. We have leveled forests and replaced them with farmland that feeds billions. We have connected every continent with networks of roads, cables, and air routes. We behave as though the Earth belongs to us, as though we have conquered it, catalogued it, and understood it. The ocean tells a different story. The ocean tells us that more than 70% of the Earth's surface is covered by water, and that beneath that water lies a world we have barely begun to explore. The Devil's Sea is not an anomaly. It is a reminder. It reminds us that beneath the familiar surface of the planet lies a world that is alien in every meaningful sense. A world of crushing pressure, absolute darkness, extreme temperatures, and geological violence that operates on scales that dwarf anything on the surface. We do not understand this world. We have sampled it, probed it, and sent robots into its margins. We have measured its pressure, recorded its temperature, catalogued some of its life forms, but we have not understood it. Not in the way we understand the surface, where we can predict weather systems days in advance, track the movement of animals across continents, and model the growth of forests over decades. The deep ocean does not submit to prediction. It is too large, too complex, too remote, and too hostile to human presence. Every expedition into the deep is an exercise in humility. The pressure destroys equipment. The cold drains batteries. The darkness makes observation impossible without artificial light that must be carried at enormous cost in energy. The distance from the surface means that any failure of equipment or judgment can be fatal. The deep ocean does not forgive mistakes, and it does not offer second chances. The disappearances in the Devil's Sea are a symptom of this ignorance. Ships vanished because they sailed into waters whose dangers were not understood. The seafloor was unstable, but the charts did not show it. Volcanoes were erupting beneath the surface, but no monitoring system detected them in time. Methane was erupting from the seabed, but no one knew the deposits were there. The ships and their crews paid the price for knowledge we did not yet possess, and the ocean kept their remains. In the years since the peak of the Devil's Sea disappearances, our technology has improved substantially, but the gap between what we know and what we do not know remains enormous. We have developed remotely operated vehicles that can descend to the Haddle Zone and return with high-definition video and geological samples. We have deployed arrays of hydrophones across entire ocean basins that can detect submarine volcanic eruptions and earthquakes as they happen. We have launched satellites that measure sea surface temperature, wave height, and ocean color with daily global coverage. These are powerful tools, but they are expensive. Their coverage of the deep ocean is sparse, and the ocean is so vast that even our best instruments can only sample a tiny fraction of its volume at any given time. The Devil's Sea, with its combination of extreme depth, active volcanism, and tectonic instability, represents some of the most challenging conditions the deep ocean has to offer. Exploring the seabed in this region is not simply a matter of sending a submersible to the bottom and looking around. It requires navigating through water columns that may contain volcanic gases, landing on surfaces that may be unstable or actively erupting, operating instruments in magnetic fields that may interfere with electronic systems, and doing all of this at distances from the surface that make rescue impossible if anything goes wrong. It is an extreme environment by any measure, and yet it is not remote in the way that Antarctica is remote, or the Mid-Atlantic Ridge is remote. It is located within a few hundred kilometers of one of the most technologically advanced nations on Earth. Japan has the resources, the expertise, and the motivation to explore the Devil's Sea in detail. And yet the deep seabed of the region remains largely unexplored, its hazards incompletely catalogued, its behavior incompletely modeled. There is a philosophical dimension to this that deserves attention. The Devil's Sea challenges the narrative of human mastery over nature. We like to believe that the age of exploration is over, that there are no blank spaces left on the map, that every mystery has been solved or will be solved by the next generation of instruments and algorithms. The Devil's Sea says otherwise. It says that there are places on this planet where the Earth itself is hostile to human presence, where our technology is insufficient, our knowledge is incomplete, and our confidence is misplaced. It says that the map still has blank spaces, and that some of those blank spaces are not in distant galaxies or on the surfaces of other planets, but directly beneath our own ships, a few hundred meters below the keels of the vessels we rely on to carry our goods, feed our economies, and connect our civilizations. The ocean does not care about human ambition. It does not care about our ships, our instruments, or our theories. It operates according to physical laws that are indifferent to our survival. The volcanic eruptions beneath the Devil's Sea will continue whether or not we understand them. The methane deposits will continue to accumulate and, occasionally, to erupt. The tectonic plates will continue their collision at a rate that is imperceptibly slow by human standards, but unimaginably powerful by any measure. And the ocean will continue to be deep, dark, and cold, regardless of what we do on its surface or say about it in our textbooks. The story of the Devil's Sea is ultimately a story about limits. The limits of technology, the limits of knowledge, the limits of human courage when confronted with forces that operate on scales we cannot directly perceive. We have explained some of what happens there. We have identified the hazards and built models and published papers and held conferences. But we have not explained everything, and the part that remains unexplained is not a footnote or a minor residual mystery. It is the central question. Why do ships vanish completely, without warning, without wreckage, without survivors, in a region that has been studied for more than 70 years by some of the most capable scientists and institutions on Earth? The answer may be that the Devil's Sea operates as a system too complex for our current tools to fully unravel. The answer may be that we need new instruments, new methods, new computational models, and a new willingness to invest in ocean exploration at the same scale we invest in exploring other worlds. The answer may be that some of the ocean's secrets will resist disclosure regardless of our efforts, because the ocean is simply too vast and too powerful and too hostile for any single species, no matter how clever or determined, to fully comprehend. Whatever the answer, the Devil's Sea is not finished with us. The forces that shape it are still at work. The plates are still grinding. The volcanoes are still building. The methane is still accumulating in the cold sediments of the deep seabed, and the ocean is still dark, still deep, still indifferent to the ships that cross its surface and the lives that depend upon their safe arrival. What does the Devil's Sea mean for the world as it exists today? On one level, it means that the ocean is more dangerous than most people realize, even in an age of advanced technology. We live with satellite navigation, weather forecasting systems that can predict storms days in advance, and real maritime monitoring networks that track the position of every large vessel on the planet through the automatic identification system. We have contingency plans for typhoons, tsunamis, and oil spills. We have search and rescue protocols that can deploy aircraft and vessels to a distress call within hours. And yet, all of these systems operate at the surface or above it. They tell us about the skin of the ocean. They tell us almost nothing about what lies beneath. The global economy depends on the ocean to a degree that most people do not appreciate. Approximately 90% of international trade by volume is carried by sea. Every day, thousands of cargo ships, tankers, bulk carriers, and container vessels cross the world's oceans, carrying goods worth billions of dollars. The clothing on your back, the device you are reading this on, the fuel in your car, and the food in your refrigerator have almost certainly spent time in the hold of a ship, traversing thousands of kilometers of open water. These ships pass over trenches, seamounts, volcanic arcs, and methane deposits that have never been fully surveyed. Most of the time, this does not matter. The hazards are localized, the ocean is vast, and the probability of any single ship encountering a catastrophic seabed event is extraordinarily small. But the probability is not zero. It has never been zero. And the Devil's Sea is a permanent, documented reminder of what can happen when statistical improbability meets physical reality. There is also the question of undersea infrastructure. The modern world is connected by a network of submarine cables that lie on or just beneath the ocean floor. These cables carry the internet. More than 95% of intercontinental data traffic passes through fiber optic cables laid across the seabed, and many of these cables cross regions of geological activity. A submarine volcanic eruption, an undersea landslide, or a seismic event along a cable route can sever the connection, disrupting communications and financial transactions across entire continents. This has happened. Submarine cables have been damaged by earthquakes and underwater landslides in the past, and the repairs are expensive, time-consuming, and dependent on specialized ships that are in limited supply worldwide. The Devil's Sea is a reminder that the infrastructure we depend on is vulnerable to forces we do not fully understand and cannot fully predict. There is a lesson about complacency embedded in the Devil's Sea story. The disappearances peaked during a period when the region was heavily trafficked by fishing vessels and merchant ships following established routes. The ships were doing what they had always done, sailing through waters that appeared no different from any other part of the ocean. The danger was invisible. It lay beneath the surface, in the chemistry of the water, the magnetism of the rock, the pressure of the gas, the heat of the volcano. The ships had no instruments capable of detecting these hazards, and their crews had no warning of what was about to happen. They were, in a sense, complacent, not out of negligence, but out of ignorance. They did not know what they did not know. We face an analogous situation today, on a global scale. We have mapped the surface of the ocean with impressive precision. We have charted shipping lanes and modeled current systems and built weather prediction algorithms that save thousands of lives every year. But beneath the surface, vast stretches of the seabed remain unknown. We do not have a complete inventory of active submarine volcanoes. We do not know the full extent of methane hydrate deposits worldwide. We do not know where the next major submarine earthquake will occur, or what secondary effects it will produce, which seamounts will be destabilized, which gas deposits will be disturbed, which cables will be severed. We are sailing, collectively, over an abyss of incomplete information, and the only thing protecting us is the statistical improbability that any individual ship, on any individual voyage, will encounter the worst that the seabed can deliver. Probability is a shield, but it is not a wall. The Devil's Sea proved that. There is also a deeper implication, one that touches on the nature of knowledge itself. The Devil's Sea has been studied for more than 70 years by some of the most capable scientists and institutions on Earth. They have produced hundreds of papers, deployed sophisticated instruments, and conducted risky expeditions into dangerous waters. They have advanced our understanding significantly. They have identified the hazards, quantified many of the risks, and developed monitoring systems that have unquestionably reduced the danger to shipping in the region. And yet the fundamental mystery persists. We know more than we did in 1952, but we do not know enough. The gap between what we know and what we need to know has narrowed, but it has not closed. This is humbling in a way that transcends the specific case of the Devil's Sea. We live in an age of extraordinary scientific achievement. We have decoded the human genome, detected gravitational waves from colliding black holes billions of light years away, and photographed the shadow of a supermassive black hole at the center of a distant galaxy. We have developed vaccines in record time, built artificial intelligence systems that can compose music and write prose, and landed robotic explorers on Mars and on the surface of a comet. We have accomplished things that would have been dismissed as fantasy a century ago. And yet, we cannot fully explain why ships disappear in a patch of ocean a few hundred kilometers from Tokyo. The Devil's Sea is a reminder that the world and our own planet are under no obligation to be easily comprehensible. The ocean does not owe us its secrets. There is a pause worth taking here, a moment to consider what it means to live on a planet we do not fully understand. We walk on its surface with confidence. We build structures that reach toward the sky. We dig tunnels that burrow into its crust. We launch vehicles that escape its gravity. We behave as masters. But the Devil's Sea whispers a different truth. It whispers that, beneath the surface, beneath the ocean, beneath the thin crust of rock and soil on which we have built our civilizations, there are forces at work that are older than human civilization, larger than human comprehension, and indifferent to human survival. These forces shape the land we stand on and carve the trenches we cannot reach. They built the mountains and opened the seas. They will continue their work regardless of what we build or discover or believe. The philosopher might say that the Devil's Sea is a mirror, reflecting our own smallness and fragility against the immensity of geological time and geological power. The ocean does not need us to understand it. It existed for billions of years before we appeared, and will exist for billions of years after we are gone, assuming the planet endures that long. What the Devil's Sea offers is a chance to remember this truth, to set aside the comfortable assumption that we have tamed the world, and to acknowledge that the world remains, in many of its most fundamental aspects, wild and unknown and beyond our control. This is not despair, it is honesty. It is the kind of honesty that leads not to paralysis but to action, to the recognition that the deep ocean deserves the same investment of resources and attention that we have lavished on the surfaces of other worlds. The seafloor of our own planet is as worthy of exploration as the plains of Mars, and far more relevant to our immediate future. The data it contains about geological hazards, biological resources, and climate processes is directly relevant to human survival in a way that Martian geology, however fascinating, is not. The 31 people who sailed aboard the Kaio Maru No. 5 did not die in vain if their loss inspires a deep commitment to understanding the forces that took them. The moral case for ocean exploration is not complicated. We live on an ocean planet. The ocean covers more than 70% of the Earth's surface. It regulates our climate, produces much of the oxygen we breathe, absorbs a significant fraction of the carbon dioxide we emit, and provides food and livelihood for billions of people. It is the single most important system on our planet, and we have explored less than a quarter of its floor. By any reasonable standard of priorities, the deep ocean should be among the most heavily funded areas of scientific research on Earth. That it is not reflects a failure, not of capability, but of imagination. A failure to see past the darkness and the pressure and the distance, and recognize that the ocean floor is not a wasteland. It is a frontier, and like all frontiers, it rewards those who are bold enough and patient enough to explore it. The Devil's Sea holds its dead, but it also holds its lessons. And the most important lesson may be the simplest one. The ocean is not ours. We are its guests, sailing on its surface, peering into its depths, and hoping that it will continue to tolerate our presence. The Devil's Sea reminds us that this tolerance is not guaranteed. It never was. It never will be. The Devil's Sea still lies where it has always lain, in the Western Pacific, south of Tokyo, above its restless geology, beneath its indifferent sky. The water there looks no different from the water anywhere else in the open ocean. It is grey when the clouds are low and blue when the sun breaks through. Waves roll across its surface as they do across every ocean on Earth. Seabirds pass over it, clouds form and dissolve above it. To a casual observer, there is nothing to mark this place as different from the million square kilometers of ocean that surround it. It is simply ocean, just water. But it is not just water. Beneath that surface, the Earth is speaking in a language older than any human tongue. It speaks in the language of tectonic pressure and volcanic heat, in the grammar of methane and magnetism and shifting stone. It speaks in eruptions that no one sees and earthquakes that no one feels, in the slow accumulation of stress along fault lines that were old when the first fish swam and will be active when the last fish dies. It has been speaking for longer than human memory can reach, for longer than the existence of our species, and it will continue to speak long after the last ship has passed through its waters and the last chart has been drawn. The Devil's Sea is a place where the Earth's voice is loud enough to be heard at the surface, where the forces that shape the planet manifest in ways that are visible, measurable, and sometimes fatal. Most of the ocean floor speaks in the same language, but quietly. In the Devil's Sea, the Earth raises its voice. The ships are gone, the Kaio Maru No. 5 and its 31 souls. The fishing trawlers that sailed out and never came back, their names fading from memory as the decades pass, their families left with nothing but absence and questions. The merchant vessels that sent no distress calls, left no wreckage, offered no explanation. They are at the bottom now, if anything of them remains, resting on a seabed that is itself never at rest. The hulls are dissolving in the cold, corrosive water of the deep. The steel is rusting, the wood rotting, the metal fittings being slowly consumed by the patient chemistry of the ocean. In a few more decades, there may be nothing recognizable left. The ocean takes everything eventually. It takes ships and bones and memory and name, and it gives back nothing but silence. The ocean above those wrecks is dark, not the darkness of a room with the lights turned off, which retains the memory of light and the promise of its return, but a fundamental, permanent darkness that has never been interrupted by a single photon of sunlight. It is the darkness of the abyssopelagic zone, the darkness of a world that exists in perpetual midnight, where the only illumination comes from the cold blue-green glow of bioluminescent organisms, living things that have evolved to make their own light, because no other light exists. In this darkness, the pressure is immense, the temperature barely above freezing, and the geology beneath continues its slow, violent work, building and destroying, rising and sinking, in a cycle that has no end and requires no audience. We tell their stories not because we can bring them back, but because their stories illuminate something true about the world and about ourselves. They illuminate the limits of human knowledge and the scale of human ignorance. They remind us that courage is not the same as safety, that knowledge is not the same as understanding, and that the ocean, for all its beauty, is not a place that was made for us. We did not evolve in the ocean. We left it millions of years ago, crawling onto land and never looking back, and the ocean has changed without us, deepened and cooled and filled with life that owes nothing to the sun. We survive it by skill and by luck, and by the accumulated wisdom of generations of sailors who learned, often at terrible cost, where the dangers lie and how to avoid them. And in the Devil's Sea, the danger lies everywhere, above the seabed and within it, in the water and in the rock, in the current and in the calm. It lies in the chemistry of the deep water and the magnetism of the volcanic stone. It lies in the methane that sleeps in the cold sediment and the magma that seethes beneath the crust. It lies in the interaction of these forces, an interaction that we have described but not predicted, catalogued but not controlled. The Devil's Sea is not a mystery that will be solved by a single discovery or a single expedition. It is a permanent feature of our planet, as real and as enduring as the mountain ranges and the river systems and the atmosphere itself. Its dangers are not supernatural. They are geological and chemical and physical, rooted in the same processes that have shaped the Earth for 4.5 billion years. They are rooted in the same forces that built the islands of Japan that carve the Pacific trenches to depths that beggar imagination, that continue to drive the immense plates of the Earth's crust in their slow, relentless dance across the face of the planet. These forces are not malevolent, they are not even aware. They have no intention, no purpose, no design. They are simply the mechanics of a planet that was never still and will never be still, a planet whose interior is hot and whose surface is cold, and whose ocean fills the space between with darkness and pressure and salt. What we can do, and what we must do, is continue to learn. Map the seabed with greater resolution. Monitor the volcanoes with more sensitive instruments. Study the methane deposits with more thorough surveys. Model the interactions between geological, chemical, and hydrodynamic processes with greater computational power and more comprehensive data. Each increment of knowledge makes the ocean a little less dangerous, a little more navigable, a little more comprehensible. The Japanese surveys of the 1950s saved lives by revealing hazards that were previously unknown. The monitoring of Myojinsho has prevented ships from sailing into active eruption zones. The Sunderland research on methane-induced sinking has informed safety protocols for vessels operating near known gas deposits. Knowledge works. Understanding protects. The Devil's Sea challenges us not to conquer it, for it cannot be conquered, but to respect it, to approach it with the humility that it demands and the patience that it rewards. The ocean is vast. It covers more surface area than all the continents combined. It is deep. Its average depth exceeds 3,500 meters, and its greatest depths approach 11,000 meters. It is dark. Sunlight penetrates less than 1% of its volume. It holds more than we have ever imagined, more than we can currently catalogue, more than we have the instruments to detect, or the models to predict. And the Devil's Sea is only one small part of its immensity, but it is a part that has earned its name. A part that has taken what it wanted and kept what it took. A part that reminds us, with a patience that is almost gentle, that the Earth is not a stage for human drama. It is a living, active, restless planet, and we are small upon its surface, fragile in its waters, and blind to the greater part of what lies beneath. There are other Devil's Seas. They have different names and different locations, but they share the same geology. The Bermuda Triangle, for all the mythology that has been heaped upon it, sits above the Puerto Rico Trench, the deepest point in the Atlantic Ocean, in a region of active seismicity and known methane deposits. The waters off the coast of Norway, where ships have disappeared for centuries, sit above some of the largest methane hydrate deposits in the world. The Sunda Strait between Java and Sumatra, one of the most volcanically active straits on Earth, has claimed ships for as long as ships have sailed there. These regions are not connected by any supernatural force. They are connected by geology. They are places where the internal energy of the Earth reaches the ocean floor with sufficient intensity to affect the surface, places where the boundary between the solid Earth and the liquid ocean is thin, active, and unstable. The Devil's Sea is the most famous of these regions, but it is not unique. It is a representative. It speaks for all the places on Earth where the ocean and the geology conspire to remind us of our limitations. The water in the Devil's Sea is calm tonight. The waves are low. The wind is quiet. The stars, if they are visible above the cloud layer, are reflected on the surface as tiny points of light floating on the darkness. There is no sound but the wind and the water, and the slow, deep pulse of the Earth moving beneath the ocean floor. A pulse that is too low for human hearing, too slow for human perception, but as real and as constant as the heartbeat in your chest. Beneath that surface, the volcanoes wait. The methane accumulates in its crystalline cage of ice and pressure. The plates grind against each other with a force that human hands cannot equal, and human machines cannot replicate. The Devil's Sea is patient. It has been patient for longer than human memory, longer than human civilization, longer than the existence of our species. And it will be patient still when the last of our questions have been asked, and the last of our ships have sailed, and the last of our theories have been published and forgotten. In the end, the Devil's Sea does not ask to be understood. It does not ask to be feared. It does not ask anything of us at all. It simply exists, as it has always existed, as it will continue to exist long after we have gone. A patch of ocean, a stretch of dark water over darker stone, a place where the earth speaks, and the ocean listens, and the surface is quiet, and the deep is not. The silence of the deep is not empty, it is full. Full of pressure, and heat and motion, and life and death, full of forces that move without sound, and act without warning, and destroy without malice. Full of creatures that glow in the darkness and feed on poison, and thrive under pressures that would crush anything built by human hands. The Devil's Sea is one doorway into that silence. There are others, scattered across the ocean floor, in every ocean and every sea, waiting to be found, waiting to be understood, waiting with the infinite patience of geology for the brief, curious species that walks the surface of this planet to look down and pay attention. The darkness waits, the ocean holds its breath, and somewhere far below the surface where no light has ever reached and no human voice has ever been heard, the earth continues its ancient, patient, indifferent work, shaping and reshaping the floor of the sea, building mountains that no human will ever climb, carving valleys that no human will ever walk, creating and destroying with a power that makes human ambitions seem very small and very brief, like a candle flame held up against the night. The Devil's Sea does not care that you have heard its story. It does not care that you know its name. It will not behave differently because you have listened. The volcanoes will erupt on their own schedule. The methane will release when the chemistry demands it. The plates will move at the rate the physics requires. The ocean will remain dark and deep and cold, regardless of how many words are spoken about it or how many pages are written. But you are different now than you were before you heard this story. You know something you did not know. You know that beneath the surface of the ocean, beneath the familiar blue of every photograph taken from space, beneath the waves that break on every beach you have ever walked, there is a world that does not answer to us. A world that is ancient and active and indifferent and powerful beyond any scale that human experience can provide. A world that has swallowed ships without explanation and kept them without apology, and will do so again, not because it is evil, but because it is the earth. And the earth does what the earth does, and we are guests in its ocean, and the rent is paid in respect, and the penalty for forgetting is absolute. The Devil's Sea is quiet tonight, but it is never still.